Hello, everyone.
Hi.
Good to see everybody. If you would, please type your first name or your nickname into chat for me. Thank you very much. It's nice to see you guys on a Thursday. I'll try to get you out of lab as fast as I can because it's such a gorgeous day. Oh, if you haven't had a chance to get out, try to take a little walk or something after class because it's lovely. Very warm and sunny and lovely. All right, very good. Still missing a few people, but we will see if they'll come in a bit. So today we're going to have a second laboratory exercise about controlling the growth of microbes. This exercise is about specifically chemical control of the growth of microbes. There are other methods, as discussed in lecture, heat and other physical methods, chemical methods, and of course, we also have drugs for controlling the growth of microbes inside the body, and those are what we call antimicrobial drugs. But today, for lab anyway, we're going to be focused on chemicals, and we're going to focus on a type of chemical that we refer to as a disinfectant. And we'll talk about not so much individual disinfectants, there are many of them, but rather families or classes of disinfectants. And we'll talk about what they do to control the growth of microbes, what their mechanism is. We'll talk about how good they do their job, how effective they are, how we can test a chemical to know how effective it is as a disinfectant, and what some of the drawbacks are for each disinfectant, each group of disinfectants. What are some of the limitations about its use that we need to be familiar with if we're going to be in the business of choosing particular chemicals for, let's say, in our workplace. There are people whose job it is, or part of their job in a healthcare setting, is to monitor for the growth of microbes in the hospital or the doctor's office or whatever other location. We've talked about that. And when we're trying to prevent the growth of pathogens, we've got to know how to do it. We've got to know how to be as effective as possible in doing that. So we have to know these different classes of chemicals. As I said, there are hundreds and hundreds of disinfectants on the market available to us, both commercially and also residentially. We've all learned a little bit about disinfectants this year, including people who've never really thought about microbes before. As we have faced the pandemic, we've had to think about things like disinfecting our homes to protect ourselves from viral infection. So that will be our objective today for the lab. Before I get started in the exercise, does anybody have any questions about anything? Any questions about anything that you're watching for lecture, or any quiz questions, or anything else that you would like to bring up? Feel free to type it in the chat and we can talk about it. Okay. All right. So I'm going to pull up our slide set for today. And that's what you should be seeing on your screen right now, a slide that says controlling microbial growth with chemicals. So our objectives for the exercise are to, again, look at these four most common families of disinfectants. There are lots of chemicals that we could, in theory, used to control microbial growth, but they have so many limitations or they're so toxic, we don't use them. So we're going to look at the 4 commonly used ones. We're going to compare their effectiveness, where they're particularly effective, where they're less effective, and then we're going to talk about their limitations. And as I said a moment ago, we're also going to think about how we test a chemical. What can we do if, say, a new chemical comes to market? How do the evaluators determine if a chemical meets the definition of a disinfectant? We have to be able to understand what kind of testing goes into that process. So let's start with just a little bit of a vocabulary review. There are a couple of terms that we need to be familiar with specifically today. And again, we discuss a lot of this vocabulary in the lecture. The term disinfectant means something very precise. It means that this is a chemical or a physical method or some kind of a molecule that's capable of eliminating common pathogens from innate objects and surfaces. So it is getting rid of the kinds of microbes that cause disease in humans, the most common kinds of microbes that cause disease in humans. And a really important part of that definition is right here. We use disinfectants on inanimate objects, okay, surfaces, objects. We do not put disinfectants on ourselves to control microbes. In other words, we don't use disinfectant chemicals on our skin. And of course, you would never take a disinfectant chemical internally. I don't know if you remember, but earlier in the pandemic, there was quite a stir when President Trump got up in front of a camera and sort of mused publicly about how he had read or he had learned that alcohol and bleach are good disinfectants. And he turned to Dr. Blix on the stage and he said, you know, that might be something we want to consider, using disinfectants in the body to clean the body of the virus. He's going to be remembered for saying that because, of course, anybody who understands what a disinfectant is understands that they are not used internally. These are chemicals that would harm you if you took them internally and even kill you. And sadly, for a few weeks after that press conference, people were reporting to emergency rooms all around the country having swallowed bleach, having tried to inject, having tried to inject bleach into their body. And of course, they suffered the consequences of that. But yeah, it's important to remember that anything that we're going to call a disinfectant is not used internally. Now, there are chemicals that are disinfectants that you can also use as an antiseptic. When we use that word, we're talking about a chemical that can be used on the skin. So an antiseptic is what you might apply, say, to a wound in order to try to control any microbes that might be in the wound before you bandage it up or suture it up. There are some chemicals that are both disinfectants and antiseptics, but they're generally formulated a little bit differently. So again, you would never use a disinfectant internally. You wouldn't even use an antiseptic internally. They're not intended for that purpose. Now, the other terms we have to be familiar with are these terms down at the bottom of the slide: bactericidal and bacteriostatic. That term "cidal" means death or killing. So a disinfectant that is bactericidal is capable of killing bacteria. In comparison, something that is listed as being bacteriostatic is not actually killing the bacterial cells, but rather stopping their growth. So that's an important distinction. You hear those two terms used most commonly when people are talking about antimicrobial drugs. So things that we do take internally, because there are whole classes of antimicrobial drugs that are bactericidal and other classes that are bacteriostatic. And you might think that a bacteriostatic drug isn't very good because it doesn't kill bacteria outright. But the truth is, a bacteriostatic drug is just as useful in many situations because by stopping the growth of the cells, and remember that means the division of the cells, the numbers of bacteria are kept constant. And what happens when you take a bacteriostatic drug, for example, is you're giving your immune system a chance to get on top of the infection. One of the reasons that infections really get out of control and patients get so sick is because when bacteria start to grow, they divide exponentially if conditions are good. So very quickly you go from just a handful of cells to millions of cells. And the immune system can sometimes really get overwhelmed by the infection. When you take a bacteriostatic drug, you're holding the number of cells constant at a lower level, and you're giving the immune system a chance to do its work. The fact is that antimicrobials are not effective unless the person has a functioning immune system. So we want to think that antibiotics are what save us when we get infected. But in reality, the antibiotic is working to help the immune system do its job. We learned this, especially, or I should say, we were reminded of this during the AIDS epidemic. People who came down with the human immunodeficiency virus and developed AIDS early on in that epidemic were getting infected with, all kinds of different pathogens, and physicians would prescribe antimicrobial drugs, antibiotics, and others, and the patients would still die. And it was a reminder to us that it's not the drug that's saving you, it's your immune system that's saving you. The drug is helping. It's helping your immune system do its natural work. So if you don't have a functioning immune system like an AIDS patient does not have, even the strongest, most powerful antibiotic won't save you. You have to have the immune system behind you to ultimately control infection. So two terms that are associated with different antibiotics and antimicrobial drugs, as well as disinfectant chemicals. Now, one of the things that's important to know as you're learning about disinfectants is there is no one perfect disinfectant. Okay, there's no one chemical that's going to be perfect in every situation. The reason we have so many is because of this, because under different circumstances, different families of chemicals work better. So we have to remember that there is no perfect disinfectant. Again, during this pandemic, there was a lot of public discussion about disinfection. How do I disinfect my house? How do I disinfect my groceries? How do I disinfect my car? And everybody wanted to know what the best one was. And of course, the answer is there is no best one, because all disinfectants have certain limitations associated with them. We have to know these details because we have to be able to match the disinfectant chemical with whatever it is we're trying to achieve. What is the environment that we're trying to disinfect? What kind of materials are we trying to disinfect? What are the potential pathogens that we think might be present in the environment? The pH, the solubility of these chemicals, the toxicity of these chemicals, whether or not we're talking about like a metal surface or whether we're trying to disinfect a softer, more organic surface, all of those things matter. Even in terms of organic matter, even the presence of soil and dirt matters with disinfectants. If you want to disinfect, let's say a floor, the first thing you need to do is clean the floor. You need to get all the dirt and grime off of the floor first and then disinfect it, because organic matter, soil, dirt, just things from the environment might interfere with that chemical. So we need to get all that stuff out of the way first and then disinfect. The other thing for us to always remember is that any one chemical can be very effective and very useful against one particular kind of pathogen and completely ineffective against another. So again, you have to know what environment you're trying to clean, what materials you're trying to disinfect, and what pathogens you think you are dealing with. That's why it's so important to monitor the environment for pathogens. So when a chemical comes to market, if it wants to get labeled as a disinfectant, at least in our country, it has to go through certain testing processes in order to be able to put that word on the label. There are a couple of different ways that this is done, that these tests are conducted, but one of the most common generates a number called the decimal reduction time. Now, this is often abbreviated DRT. So if you look into textbooks for DRT values, it doesn't usually say decimal reduction time. It says DRT. There is also another term that's used, and that's the D value. So if you ever see that in a table, that just means decimal reduction time. What the decimal reduction time is a calculated quantity. So this is a quantitative assessment. It's the time, specifically in minutes, that are required to kill 90% of the microbial cells in a particular sample. So these chemicals get evaluated in the laboratory. A certain number of cells gets exposed to the chemical, and a timer is started. And then they sample periodically to see how many cells are still alive. And when 90% of the cells in the sample are gone, are dead, that's your DRT. And you'd be amazed how DRTs differ from the way people often use disinfectants. Think about how people generally, let's say, disinfect a kitchen counter. Again, there are so many products on the market. It's crazy. All you have to do is walk into a supermarket and go down the aisle where all the cleaning chemicals are. And if you start looking at labels, there are lots of products. And people buy these products, you know, thinking that they want to disinfect their home, all the surfaces in their home. But think of how people typically do it. I mean, what you expect them to do is to spray the surface. You know, they'll spray their kitchen counter and then they'll take some paper towel or a rag and they'll immediately wipe it off. And the truth is, when you start to look at DRT values, they're not really disinfecting. What they're doing is going to help, right? I mean, just physically wiping a counter is going to pull cells off of it, right? But a lot of times what people think is disinfection is not really. It would be a lower category, something more like sanitizing, sanitizing their counters. DRT values are a lot longer than most people would think. Take a look at this table. This comes out of a reference text. It lists several disinfectant chemicals on the far left. And then it lists in the next column some bacterial species that these chemicals were tested on. You can see the concentration that the manufacturer recommends against each of these different organisms. You've got some quantitative values in the rest of the table, including this one right here. This is the D value. This is the DRT. This is the time in minutes that it takes this chemical to kill 90% of the cells in a particular sample in the laboratory. So take a look at the first one, hydrogen peroxide at 10%. Hydrogen peroxide, as we've said in here, is toxic. It's toxic to living cells. So remember, they've tested these 3 different organisms, the Pseudomonas, this Bacillus, and a Staphylococcus, at the manufacturer's recommended concentration. Look at the D value. If you're fighting against Pseudomonas aeruginosa, for hydrogen peroxide, it's 3.8 minutes. So you would have to, let's say, spray your kitchen counter with hydrogen peroxide and let it sit for 3.8 minutes in order to reduce the number of Pseudomonas cells, if they're there, by 90%. And it only goes up from there. Look at the Bacillus subtilis is 5.6 minutes. For Staphylococcus aureus, 8.7 minutes. You would have to spray the hydrogen peroxide and let it sit for 9 minutes. Who's going to do that? Nobody's going to do that, which is why it's not common to see hydrogen peroxide sold as a disinfectant, right? Very, very few people. I don't think I know anybody who uses hydrogen peroxide as a disinfectant. Now, lots of people use it as an antiseptic, right? Lots of people will pour hydrogen peroxide on a cut because it's very effective as an antiseptic, but not so great as a disinfectant. It's not that it doesn't work. It works. It'll kill pathogens. It's that it takes too long. It's not a very practical chemical for use as a disinfectant. All right, so there are lots and lots of these tables published with D values or DRT values. And again, if you, as part of your job, if you were responsible for picking and choosing disinfectant chemicals in order to disinfect a workplace, you would have to know how to read these charts. You would have to know how to interpret this so that you could make the best choice of chemical for your particular situation. Now, there is another test. It's one you should just be familiar with. It's referred to as the Use-Dilution Test. And this test was developed by a group called the American Official Analytical Chemists, or the AOAC. Now, the Use-Dilution Test, similar to the DRT, is going to take this chemical and it's going to use it at the manufacturer's recommended dilution, but it's going to do the test quite differently than the DRT. The test organisms typically include a couple of the same ones that we just saw in that table, Pseudomonas, Staph aureus, but also usually something like Salmonella, some kind of a fecal intestinal organism is typically part of this test. The procedure involves, in the laboratory, growing pure cultures of these organisms specifically. And once you have the pure cultures, you take these little steel cylinders, and I'll show you these in a minute. These are referred to as carriers. These are sterile, they're steel, they're small. They get dropped down into the broth culture and then taken back out and allowed to dry. So essentially, we're coating these steel cylinders in bacterial cells. Then you take the dried steel cylinder and you place it into a disinfectant solution, again, at the recommended dilution for the recommended time, according to the manufacturer. Then you take the cylinder out of the disinfectant and you drop it down into some fresh nutrient broth to see how many cells are still alive and what you can grow. Now, doing a little bit of math, you can actually quantify what percentage of cells were killed by the disinfectant. Now, this test would only work for bactericidal products because, again, you would only be able to count if cells were actually being killed. You'd be looking at a reduction in cell number. It's the same thing with DRT. You're looking at a reduction of cell number. So this is what these little steel carriers look like. They're just little pieces of steel that are wrapped into this cylinder shape. You can see it's not sealed all the way. And these are sterilized. They're probably an inch in length, maybe a little bit less. They're sterilized and then they're dunked into the pure culture. And then they're set into these Petri dishes on top of filter paper to dry. So essentially you're coating the cylinder in bacterial cells. And then you take the cylinder and you drop it into the disinfectant. Then you're going to take it out after the right amount of time and put it into some fresh broth culture so that whatever cells are still alive, you can grow. Now, there are other tests. These are just two that you should be familiar with. There are several modifications, for example, to the Use-Dilution Test. Sometimes laboratories, instead of using the steel cylinders, they just eliminate those. And what they'll do is they'll take some broth culture and they will literally just put the disinfectant into the broth culture and leave it for the recommended amount of time. Some people think that's a more realistic test because you're going to be, as long as you know the starting number of cells that you have in your tube, it will allow all cells to be, uniformly exposed to the chemical because the chemical will disperse through the broth. And essentially what they do is they pull cells out of the tube every few minutes and put them on a plate, an agar plate, and see how many are left. So there are modifications to the Use-Dilution Test like this. There are other tests. There are some tests that are quantitative. There are some tests that are just qualitative. And remember, the difference there is a quantitative test is going to give an actual number. The DRT is quantitative. It's going to tell you how many minutes it takes to decrease cell number by 90%. But there are also qualitative tests out there, tests that will say whether a chemical can kill, if it can or if it can't. It's not going to have any numbers associated with it, but it's going to tell you whether it's capable of killing bacteria. So again, when a manufacturer wants to label their product as being a disinfectant, in our country, they have to go through these lab tests in order to prove it. They have to prove that their chemical works as a disinfectant. All right. So anybody have any questions about anything that we've talked about so far? The next time you go to the supermarket and you have a few extra minutes, go down that chemical aisle and pick up a few containers and start looking at the label. Remember, the term disinfectant means something legally in this country. So you won't always see it on a label. Some will use the word sanitize instead because sanitize is a lower standard. And it's also very interesting to look on the label for what it can disinfect against. I'll tell you a little story during this pandemic. If you remember, if you've experienced this, maybe a lot of people wanted to buy Clorox wipes. Right from the get-go, Clorox wipes were a very popular product that people wanted to buy to, again, disinfect their home. And for all of the reasons that we know of, the Clorox wipes became very hard to find. Most grocery stores, drugstores were sold out of them. People were trying to buy them on the internet, couldn't find them. A period of time went by where nobody had them. And then somewhere in the summer, a lot of grocery stores started selling their own brand of Clorox wipes. In other words, you'd walk down the aisle and you'd see one of those canisters, but if instead of being Clorox brand, it would be, Market Basket brand or Hannaford brand. And it would say something like, the Market Basket, I don't know, antibacterial wipes or something like that. If you look at the label, it will tell you what it's effective against. If it can disinfect, does it disinfect against bacteria? Does it disinfect against viruses? Does it disinfect against, fungi, things like that? And a lot of these products are not effective against viruses. So sadly, a lot of people, in an effort to do the right thing and disinfect their homes, were buying products that are not effective against viruses. So a lot of people, I think a lot of people learned a lot about disinfection during this pandemic because they were sort of forced to. They were forced to learn it. So we're going to talk about 4 groups of disinfectant chemicals. These are like classes or families of disinfectant chemicals. The first one are the alcohols. Then there are the chlorinated compounds. Think about bleach when I use that term. The third one are what are called iodophores. And the fourth group is called the Quaternary Ammonium compounds. So let's start with the alcohols first. We talked about alcohol early in the semester when we were talking about aseptic technique. Remember, we said in microbiology labs, and in fact, most labs, the disinfectant of choice is either alcohol or bleach. 70% alcohol or 10% bleach are typically what people use to clean their workspace. Alcohols include things like isopropanol. That's the one that is very commonly used in labs. We use that one at Keene State. Ethanol, any kind of alcohol can function as a disinfectant as long as it's at the right percentage dilution. So it needs to be between 60 to 90%. And again, most people who use alcohol to disinfect will use it at 70%. Undiluted alcohol is just less effective as a disinfectant. And that seems bizarre to people. They want to believe that, if 70% is good, then 100% must be better. But the truth is, the water that we add to the alcohol to dilute it actually helps the alcohol do a better job. So you really do have to dilute it in order to use it as a disinfectant. Now, alcohol is what we consider rapidly bactericidal. And what I mean by that is it's bactericidal. It kills bacterial cells in seconds. So if you go back to my example of somebody spraying and then immediately wiping it, that's okay with alcohol because alcohol works that quickly. So one of the reasons that we choose alcohol in the laboratory is because you can use it like that and it still works. It's going to destroy and kill cells within a few seconds. It's going to kill bacteria. All right. So one of the things that we'll talk about as we go through these chemicals is what their scope of activity is. And what I've done is I've pulled out a few different types of microbes and microbial structures that we might be interested in knowing whether or not a particular chemical is effective against. For example, the organism that causes tuberculosis, and that one goes by the genus Mycobacterium and the species Tuberculosis. If you recall from lecture, when we were talking about cell structure, Mycobacterium tuberculosis is a very unusual bacteria in that it can't be gram stained. It secretes this waxy material called mycolic acid. And this wax surrounds the cell and it literally prevents the gram stains, the crystal violet and the Gram's iodine, from penetrating through it to get to the cell wall. So if you try to gram stain this organism, you don't get a color. You don't get any color. You have to use a procedure called acid fast staining if you want to stain this particular bacterium. So because of that waxy material, the TB organism is a little bit harder to kill too. And not all disinfectant chemicals are effective against this organism. So if you worked in a place professionally that TB was a problem, let's say you worked in a hospital that typically encountered patients with TB. In fact, there are clinics in other parts of the world, not here so much, but in other parts of the world, there are entire clinics that are devoted to tuberculosis patients. So in a place like that, you would want to make sure that whatever chemical you were using was very effective against this TB organism. And it turns out alcohol is effective. It will disinfect against this TB bacterium. Now, the other organisms on the list or structures, there's fungi listed, there are viruses listed, and also bacterial spores. So yes, alcohols will destroy fungal cells. Alcohol will destroy viral particles. And regarding spores, alcohol is not effective. So again, you have to know your situation. You have to know what you're trying to protect against. If you are in a professional situation where it's suspected that you're dealing with a lot of bacterial spores, you have to know which disinfectant chemicals are effective at destroying bacterial spores. Remember what a spore is. It's this inanimate sort of state that a bacterial cell can put itself into, some bacterial cells. And it's essentially, it's in suspended animation. It's not metabolizing, it's not taking in nutrients, it's not secreting waste, it's not making ATP, it's just in suspended animation. And it's got this shell of material around it that keep the DNA safe so that it can become a cell again someday once the conditions improve in the environment. So again, spores may not be an issue so much in certain situations, and so alcohol is still very effective. But if spores are a concern, then you would probably not choose alcohol. Now, let's also talk about the mechanism of action of these chemicals. For alcohol, the way it works, the reason it kills bacteria and fungi and destroys viral particles is by denaturing protein. You're going to see this mechanism again and again for disinfectants. When I use that term denature, you can translate that as unfold. Alcohols are going to unfold proteins. Remember, all a protein is a long, long chain of amino acids that are all bound to each other covalently. And inside a living cell, that long chain is going to get folded up into an elaborate three-dimensional structure. And it's the structure, that folded structure, that's going to allow the protein to do a certain job. So by unfolding it, it essentially inactivates the protein. And that's what kills the cell. Now, regarding limitations for alcohol, because there are a couple. Number one is that it does damage certain materials. And you probably already have a sense of this. Alcohol is very drying. Alcohol can destroy rubber. It can destroy certain plastics. It can destroy certain types of lenses, optical lenses over time. So you have to know what it is you're applying it to and whether or not those materials will be destroyed by it over time. Something else to know about alcohol is that it's very expensive, relatively speaking. We often go to the drugstore and pick up a little, 250 ml bottle of alcohol or something like that for use in the home. But if you're using it in an industrial or a commercial situation, you're often buying it in, gallon jugs. And a jug this size, a gallon jug of pure alcohol, runs you about $100 right now. So again, you got to think about that when you're choosing disinfectants, because if you're going to try to disinfect floors in a hospital, alcohol's not going to be your choice. It would just be too expensive. It'd be much too expensive. There are cheaper options. But for smaller areas, it makes a good disinfectant. It makes a very good disinfectant. On this slide here, there's just a little drawing to reinforce the idea of what denaturing is. Remember, basically, we're talking about unfolding. So what you have over here on the left is a drawing of a folded protein. The green ribbon represents the chain of amino acids. And remember, for most proteins, we're talking about hundreds to thousands of amino acids, side by side, all covalently bound to each other. And what makes one protein different from another protein is the order that the amino acids are in. And depending on those amino acids and the order they're in, that's going to determine how a protein folds up. You can see there are these helical regions, and then there are some regions that are planar or flat, and then there are these loops of amino acids. It's a very intricate structure. And the structure is completely dependent, or I should say the function is completely dependent upon that structure. If you change the structure, you're going to change the function. So by unfolding that protein, you've destroyed its ability to do its job. All the amino acids are still there. They're all still attached to each other in a long chain, but the folds are gone. So there's no more three-dimensional structure to it, and it just can't do its job anymore. And because proteins are one of the most critical molecules in a living cell, they're involved in so many of the functions that go on every moment of every day. By denaturing proteins, you kill the cell very fast. I put this drawing in just to remind us about spores. Alcohols are very effective at denaturing protein, but that's not going to be useful when we're fighting against a spore. Because essentially what a spore is genetic material from a cell that gets surrounded by layers and layers and layers of impenetrable materials. A spore, the purpose of a spore is to keep that genetic material safe until the conditions in the environment are good again and promote the health and the growth of living cells. So alcohol just doesn't help us when it comes to destroying spores. All right, so those are the alcohols. Next on the list are the chlorinated compounds. And I told you to think about bleach because that's essentially what we're talking about when we talk about chlorinated compounds. What bleach is technically is a molecule called hypochlorite. And of course, bleach is a very common product used in households, in residences, as a cleaning agent, a whitening agent, and a disinfectant. We also use bleach in laboratories all the time because it's a good disinfectant. It is rapidly, again, bactericidal. So at a solution of only 10%, you can spray it on the desktop and then immediately, essentially, wipe it off, and it will still work. It'll kill cells, bacterial cells. Now, for the scope of activity, there are some differences here between bleach and alcohol. In terms of the organism that causes tuberculosis, bleach will kill that organism, but not rapidly. So again, if you're concerned about this organism in the environment you're trying to disinfect, bleach is probably not your choice. It literally takes minutes of exposure time. So you can't spray it and wipe it and kill the TB organism. For fungal cells, yep, it's good, it works well. For viral particles, once again, it'll work, but you got to put it on the surface and leave it there for several minutes. And finally, spores, it actually will work on spores. Here's the problem though. You have to use a higher concentration than what you would use to kill bacteria. So if you're using the recommended 10% solution, it's not going to kill or destroy spores for you. If you are specifically trying to destroy spores, you need a higher concentration of bleach and you need minutes of exposure time. So again, probably not your first choice. If you're trying to get rid of spores, you need something that's going to work, and it's going to work quickly and easily. Now, in terms of the mechanism of action of chlorinated compounds, believe it or not, we're not completely sure. That always amazes people when you tell them. We don't exactly know why bleach is so rapidly bactericidal. We know that it makes an acid when you put it into water. And we know that that acid product is an oxidizer. Now remember though, when we say something has been oxidized, that's different from calling something an oxidizer. An oxidizer is a chemical that goes around and steals electrons from other molecules. So an acid, the acid that's made when you put bleach into water, is going to destroy molecules by stealing electrons from them. And that may, in fact, be the only mechanism at play here. But we're not 100% sure, believe it or not. Chlorinated compounds are one of the most common commercially available disinfectants. You don't only see it sold as, a gallon of bleach, but you see all kinds of bleach mixed with other chemical spray bottle products. Clorox alone has probably dozens of different products for sale on the market that are labeled as disinfectants. It's a decent disinfectant. It's rapidly bactericidal as long as it's at the right concentration. Now, it has some significant limitations associated with it. First of all, it's less effective in any environment that has a high pH associated with it. Remember, high pH means alkaline or basic. And if Clorox bleach and other bleaches are working by becoming an acid, if you mix an acid and a base, they're just going to neutralize each other. So if you tried to use bleach in an alkaline environment, it wouldn't work as a disinfectant. It's much less effective in the presence of organic matter. And again, this is an example of be sure to clean first. If you're trying to disinfect a surface that's dirty or has a lot of, let's say, dried food stuck on it or something like that, you've got to clean it first if you're going to use bleach to disinfect it. Here's another really important thing to know. The solution gets less effective over time, and it gets less effective quickly. The recommendation is if you're going to use bleach as a disinfectant, that you only keep the solution for about a week. So if you're going to mix up a 10% solution in a spray bottle, you got to make it fresh every week. So that's a limitation to bleach. You don't have to do that if you're going to use alcohol. You can keep alcohol as a 70% solution for a long time, and it's not going to be less effective. Just like alcohol, it does damage materials, but a different list of materials. Bleach will corrode metal over time, so you need to know that. And of course, bleach is going to discolor fabrics. This is one of the reasons that people use bleach, right? Because bleach will whiten white fabric pretty nicely. But if you get bleach on colored fabric, it's going to take the color out. So probably not a huge problem for, for its use, but it's something to think about. Now, here's one other one that you may or may not be familiar with. Bleach can be very dangerous in its use in that you cannot mix it with ammonia. If you mix bleach and ammonia together, it releases an invisible toxic gas called chloramine. You don't see ammonia as much anymore in households. It used to be much more common to buy ammonia to clean your house. Like my grandmother, for example, would have used ammonia to clean her floors. It was very popular in her time. You can still buy ammonia. I've used ammonia on certain surfaces, but sometimes there's this idea that if bleach is good and ammonia is good, then maybe together they'll be even better. I mean, people think weird things. And if you mix those two chemicals together in a bucket, what will happen is the chloramine will be released and it will poison you. You will drop and you will die. And sadly, at least once a year, there's a story in the news about some poor person who mixed them and ended up dying from exposure to this gas, this toxic gas. So just something to know, you must never mix bleach with ammonia. In fact, the manufacturer says you shouldn't mix it with anything. Don't even take a chance that there might be ammonia in the thing that you're going to mix it with, and be safe. One of the nice things about bleach, especially when you compare it to alcohol, is this. It's much cheaper than alcohol. So if I was, again, buying gallons of bleach, I would be talking about dollars. A gallon of bleach is going to run you maybe $5 or $8. A gallon of alcohol is going to run you $100. And that low cost bleach, you're going to dilute all the way down to 10%. So bleach is a real bargain as a disinfectant. You have to know its limitations, but it's it's cheap to use. All right, before I go into the iodophores, does anybody have any questions about what I've talked about so far? Some people find bleach, some people love bleach. Let me say that. Some people love bleach. I've worked in laboratories where alcohol was used as the primary disinfectant. I've worked in labs where bleach was the choice. Um, I've known people who use bleach as the only chemical they use in their house to clean. They clean their bathroom with it, they clean their kitchen with it. Some people really like bleach. It works well, and they like using it. I think bleach is very irritating. I don't like it. I don't like the smell of it. I'm incoordinated enough that I always manage to get it on my clothing, and I destroy my clothing with it. So I don't personally like it, but I know a whole lot of people who professionally love bleach. Again, it just depends on what you're trying to achieve, what you're trying to disinfect, um, what pathogens you think you might be trying to kill. So, all right. So the next group, if there aren't any questions, the next group of chemicals are called the iodophores. The most important thing to know about this group is that an iodophore is not the same thing as iodine. Iodine is in an iodophore, but there are other things in there as well. So when I use that term, iodophore, that's different from plain old iodine. What they add to iodine is something referred to as a solubilizing agent. And the best way to think about this is it's something that's going to make the iodine more soapy almost. It's going to make the iodine more readily dispersible, and almost act like a soap or a sudsing agent. Now, there are lots and lots and lots of brands of iodophores, but probably one of the most common is called Betadine. And if you've worked in a healthcare setting, you may have used Betadine. Iodophores are one of the chemicals that can be used as both a disinfectant and an antiseptic. I should have mentioned that you can also use alcohol as an antiseptic, right? The last time you had blood drawn, you probably had your skin cleaned off with a little alcohol pad. Um, if you've ever, again, cleaned out a cut with alcohol, very, very common to use alcohol as an antiseptic as well as a disinfectant. And the iodophores are the same. So the generic term for something like betadine is povidone iodine. So if you see that on a label of ingredients, you know it's got iodophore in it. Now, in terms of its antibacterial action, it is bactericidal, but it is not rapidly bactericidal. Only the alcohol and the bleach are rapidly bactericidal. So if you were going to use iodophores as a disinfectant, remember we're talking about inanimate objects, you would have to put them on the surface and leave them a little bit longer, maybe a minute or two. Now, in terms of scope of activity, iodophores are effective against Mycobacterium, so that's good. They are effective against fungi, but you got to leave them on for longer, so that's a drawback. Viral particles, yes, they will destroy viral particles, and they will destroy spores, but once again, you got to leave them on. You got to leave them for minutes. As we have said before in here, it's really hard to destroy spores. Alcohols aren't going to do it at all. Bleach will do it, but only if you leave it for a long time. Iodophores will do it, but only if you leave them for a long time. So again, hard. It's hard to kill spores or destroy spores, I should say. Now, in terms of mechanism of action, It's actually the iodine that's doing the hard work. Think of the solubilizing agent as making the iodine more easy to use, but the iodine itself is what's doing the work of killing the microbe. So iodine is able to denature protein, just like alcohol does, but it's also capable of damaging DNA. So it's kind of a double hit on the bacterial cell or whatever other kind of microbial cell you're protecting against. Iodine is capable of penetrating the cell wall. Remember Graham's iodine? Remember we talked about how Graham's iodine acts as a mordant because it's capable of penetrating through the peptidoglycan in the cell wall. So it can do the same thing in an iodophore. It's going to penetrate through that cell wall and actually get into the cell. It'll denature protein and it'll damage the DNA. Now, as far as limitations of use, I'll go to the second one first. It's less damaging than the other classes we've talked about. It's less damaging overall to materials, but there's one kind of material you really can't use povidone iodine on, and that's silicone. So in a healthcare setting, silicone is used for certain types of tubing. You have to know what kind of tubing, what the material is in the tubing that you're using. Because if it's made out of silicone, you can't use povidone iodine on it or it'll destroy it. It'll like pockmark it and destroy it. Now, in terms of other limitations, this one's kind of scary. There are some species of bacteria and other microbes that can actually live in povidone iodine. They can actually survive in it. So every once in a while, you'll hear stories about a spray bottle of povidone iodine that someone is using in a lab or some other space as a disinfectant. And, somebody made it up 6 months ago or, a year ago, and nobody has thought about it since. And if you take some out and you put it on a microscope slide and look at it under the microscope, sometimes you're going to find bacteria living in there. It doesn't happen often. There aren't many species that can survive in it, but there are some. So the lesson there is if you're going to use povidone iodine, you want to make fresh solutions. Every once in a while, you don't want to use the same bottle for months and months and months and months and months because it may get contaminated and some organisms may end up growing in there. So this is kind of a complicated drawing on this slide. I don't want you to get too concerned about all the terminology, but I liked this image that the artist has drawn. This represents a bacterial cell, and they've taken away the cell wall. All we're looking at is the membrane around the cell here. You can see the heads and the tails and the heads of the bilayer of membrane. These structures represent proteins in the membrane here and here. And then if you come inside the cell, which is what this represents, you can see a representation of the DNA here and some more protein here. So up here on the outside of the cell, this molecule is the povidone iodine. And what'll happen when you use this against bacteria is the iodine itself is what's going to be able to penetrate through the cell wall and even penetrate through the membrane. Remember, there's protein in the membrane that it's going to denature. It's also going to denature proteins inside the cell, and it's going to damage the DNA. So it's a very effective bactericidal chemical because of those two abilities, denaturing protein and damaging DNA. I mentioned that it's used as an antiseptic. It's actually a very common antiseptic in healthcare situations. There are others, but a product like Betadine has been used for a long time in operating rooms. It's a nice compound for preparing the skin prior to a surgery. The surgical area will be basically scrubbed with Povidone Iodine and then generally cleaned off with alcohol. So again, a chemical that can be both a disinfectant and an antiseptic. The last group of chemicals on our list are these quaternary ammonium compounds. This is one brand name of one of these compounds called Hibiclens. You may have seen this. You may have bought this because it's commercially available now. These compounds, like the alcohols and the iodophores, can be used as antiseptics. They're very commonly used as antiseptics now. Hibiclens is a brand you'll often see in healthcare settings. The key thing about the name is that word ammonium. Ammonium is an ion. The structure of ammonium is NH4 plus. And just like we saw with the iodophores, quaternary ammonium compounds are a combination of chemicals. It's the ammonium ion that's been added with a modifying agent, something that's going to stabilize the ion, because it's the ion that's going to do the work in this compound. There are lots and lots of brand names of these compounds. Again, Hibiclens is one. There's one called Virex. That one's very commonly used in hospitals, long-term care facilities. You'll see Virex used. Rocal is another brand. This one I've seen more in veterinary application. Animal hospitals, shelters, animal shelters will often use Rocal as their disinfectant. Very, very common. Hibiclens is the brand name. The generic word for Hibiclens is chlorhexidine. So you can also find products that just use the generic term chlorhexidine. Chlorhexidine is not the only quaternary ammonium compound. There are others. In terms of the antibacterial action for these, just like we saw with the iodophores, they are bactericidal, but they're not rapidly bactericidal. You've got to allow a little contact time. You have to allow them to sit for a couple of minutes in order to be effective. The scope of activity looks very different from the iodophores. The quaternary ammoniums are not effective against Mycobacterium. They cannot penetrate through that waxy material. They do work against fungal organisms. They do work against viral particles, but here's an important note: only against enveloped viruses. And when it comes to spores, no, they are not effective against spores. If you look at the mechanism of action, they denature proteins. We see that again and again. And they also disrupt membranes. So it makes sense that they're only effective against enveloped viruses, because remember, enveloped viruses have a membrane around them. And if you remember from the lecture about viruses, animal viruses tend to be enveloped. So these compounds are still very effective as disinfectants, because we're trying to protect people against the viruses that would infect people, and those are going to be enveloped. We're trying to protect animals, again, in a veterinary situation, against viruses that will infect animals, and those are going to be enveloped. So even though they're only effective against enveloped viruses, that's okay, because most animal viruses are enveloped viruses. All right. This drawing is pretty simplistic, but it drives the point home. On the left side, up at the top, this represents a bacterial cell. And they've drawn this box here around a little section of the membrane, and then they've blown that up for us. So here's a little piece of the membrane that would be surrounding this bacterial cell. And these little red circles out here with the spikes on them, these represent those ammonium ions, the NH4 plus ions that are in quaternary ammonium compounds. And what these ions are going to do is denature protein, number one, but also disrupt the membranes. And the way they do it is because they're charged, they're ions, when they interact with phospholipids, they're going to basically break the membrane. They're going to create these little circular structures that are part ammonium and part phospholipid. And you'll end up with broken membranes. So very, very effective. Again, because it uses a double mechanism. It'll unfold all the proteins, that's good. And it will also break the membrane apart. And a cell can't live without a membrane around it. Now, there's a couple of things to know about limitations of quaternary ammoniums. They are less effective when you mix them up in hard water. So when, if you're not familiar with that term, when people talk about hard water and soft water, hard water is going to have ions in it, and those ions are going to interact with the ammonium ion and essentially inactivate it. So it's less effective in hard water. It's sold, here's Virex, it's sold as a concentrate. So you have to dilute it. You have to mix it up according to the manufacturer's directions. And if you live in a part of the country that has particularly hard water, it's probably not a good choice. Here's a limitation that I find fascinating. Quaternary ammoniums are less effective if you apply them with cotton material. So if you used a cotton mop, a mop head that was made out of cotton, or if you were going to use it as an antiseptic and you used, say, cotton gauze to spread it around, cotton, for some reason, absorbs that ammonium ion and won't let it go. So if you're going to use it, you just don't want to use it with a cotton applicator. I find that fascinating. It's a limitation. It's something you have to think about if you're going to use these compounds. The last limitation for quaternary ammoniums is one that I see more and more and more in the scientific literature. It's something I think we all need to be concerned about. We all need to think about as these compounds are used more and more in healthcare facilities. And that's this. People who are responsible for mixing up the concentrated form of the compound have reported becoming sensitized over time. So these would be the people, for example, in the hospital or the doctor's office who were responsible for perhaps custodial jobs. They're the ones who are going to be taking the concentrate and mixing it up with water in a bucket. So they're getting exposed to fumes from the concentrated product. And what has been shown in the literature is that in certain people, not everyone, but in certain people, they become sensitized to this compound over time. And it's a respiratory sensitization. So it produces something that looks a lot like asthma. In the image right here, you're looking at a drawing of a pair of lungs connected to the trachea here and the bronchi here. And what they're showing us is that in a normal bronchus, the lining is quite narrow so that you have a nice big empty space for air passage, right? But in people, again, some people who are exposed to concentrated fumes of quaternary ammonium compounds over time, this happens. The lining gets very, very thick and inflamed. And they're even showing us it's secreting a lot of mucus here. And there have been case studies in the literature of, again, janitorial workers primarily, who become so sensitized that they can't work anymore. They develop this respiratory syndrome where they are wheezing. They have to go on asthma inhalers, and they often can't work anymore. So it's a limitation for this product. It may mean that over time, either the manufacturer is going to have to sell it diluted, or they're going to have to provide these staff members with some kind of respiratory protection while they're handling this material, some sort of a respirator on their face while they're mixing it up, because that's nothing to be taken lightly. If you get sensitized to something and you develop that kind of inflammatory response, that's not something that goes away. You're going to have that for the rest of your life. So something to think about with these. You don't see this sensitization when these quaternary ammoniums are used as antiseptics, because the antiseptics are sold diluted, but the disinfectant products are sold concentrated. Yeah, it's turning out to be a bit of a problem. All right. So that brings us to the end of our discussion of these compounds. And let me ask if anybody has any questions. Has anybody ever used iodophores? Have you ever used anything like betadine in your workplace? I know some of you work in healthcare facilities. Have you ever had any experience with betadine, or have you yourself ever used it?
I've used betadine on horses before.
Yeah, we use a lot of betadine in veterinary medicine, primarily because it's not expensive anymore. It used to be more expensive than it is now, and because if you're trying to use it on a horse or a cow or some large animal, you're going through a lot of it. So yeah, we love betadine in veterinary medicine. Anybody ever use Hibiclens? I can tell you from my own personal life, I had an elective surgical procedure a few years ago, and I went in for my preoperative appointment, and I was instructed to bathe and scrub myself with Hibiclens before I went in for my surgical procedure. I had an abdominal procedure done, and I couldn't help myself. So I inquired. I'm like, oh, why are we doing this? And the instruction was that it's they're trying to be more careful now about allowing patients to come in who might have some pathogens on their skin. And by asking people to bathe with an antiseptic like Hibiclens, the chances are better that they won't carry a pathogen into the hospital. I thought it was fascinating. Um, yeah,
Did you have to buy that or did they provide it?
I actually had to go buy it. That actually didn't surprise me, to be honest. That they asked me to go buy something, it didn't surprise me. Hibiclens is not cheap either. Hibiclens is not it's not a cheap product, but I was happy to do it. And when I was waiting for my surgery, I was laughing with the nurses, the surgical nurses, because they told me when they asked me, they said, "Did you shower this morning and did you use the Hibiclens?" I said, "Well, yeah, you told me to." And the nurses said, "Oh, you'd be surprised how many people come in for surgery and have not done it. In fact, they haven't showered at all." And she's like, "This is the whole reason we've implemented this. We're trying really hard just, crack down on, the chance that somebody's going to carry a pathogen in on their skin. All right. Any questions at all about any of this? Very different topic for us today about chemicals, but a very important topic, in that if you get into any aspect of healthcare as a profession, um, you may find yourself having to, evaluate which chemicals to use in which circumstances. And it's very important that we understand our chemicals so that we know what their limitations are and where they're best used, where they're most effectively used. All right. All right. Very good. Well, that's all I have for you today. So I'm going to let you go. Hopefully, you can go enjoy a little of this gorgeous weather before it gets cold again. Um, if anybody has any questions or any issues, just send me a message. Um, and I will see you next time. All
Thank
right,
you.
everybody.
Have a good
Have a
weekend.
good night.